Do you think it's possible to do like a tiny baby network that grows into something that can do state of the art on like even a simple data set like MNIST
Oh,
and just like it just grows into a gigantic monster that's the world's greatest handwriting recognition system?
yeah. There are approaches like that. Esteban Real and Cochlear, for instance, have worked on evolving a smaller network and then systematically expanding it to a
Hmm.
larger one. Your elements are already there, and scaling it up will just give you more power.
Hmm.
So again, evolution gives you that starting point,
Yes,
and then there's a mechanism
for that.
that gives you the final result, and a very powerful approach. Um, but you could also simulate the actual growth process, and like I said before, evolving a starting point and then evolving it or training the network. There's not that much work that's been done on that yet. We need some kind of a simulation environment so there are interactions at will. The supervised environment doesn't really, it's not as easily usable here.
Sorry, the interaction
So
between neural networks.
the neural networks that you're creating, interacting the world, and learning from these sequences of interactions, perhaps communication with others. Uh,
That's awesome.
we would like to get there, but
Yeah.
just the task of simulating something is at that level is very hard.
It's very difficult. I love the idea. I mean, one of the powerful things about evolution on Earth is predators and prey emerged, and like there, there's just like there's bigger fish and smaller fish, and it's fascinating to think that you could have neural networks competing against each other, and one neural network being able to destroy another one. There's like wars of neural networks competing to solve the MNIST problem. I don't know.
Yeah, yeah. Oh,
That,
totally. Yeah, yeah, yeah. And we actually simulated also that predator prey, and it was interesting what happened there. What Padmini Rajagopalan did this, and Kay Holcomb was a zoologist. So we had again, we had simulated hyenas and simulated zebras.
nice.
And initially, the hyenas just tried to hunt them, and when they actually stumbled upon the zebra, they ate it, and we're happy. And then the zebras learned to escape, and the hyenas learned to team up. And actually, two of them approached in different directions. And now the zebras, then next step, they generated a behavior where they split in different directions, just like actually gazelles do when they are being hunted. They confuse the predator by going in different directions. That emerged, and then more hyenas joined and kind of circled them. And then when they circled them, they could actually herd the zebras together and eat multiple zebras. So there was like an arms race of predators and prey, and they gradually developed more complex behaviors, some of which we actually do see in nature. And this kind of coevolution, that's competitive coevolution, it's a fascinating topic because there's a promise or possibility that you will discover something new that you don't already know. You didn't build it in. It came from this arms race. It's hard to keep the arms race going. It's hard to have rich enough simulation that supports all of these complex behaviors. But at least for several steps, we've already seen it in this predator-prey scenario. Yeah.